So hi everybody, I'm Falcou. I will make today a presentation about a subject which is maybe something that actually reach out to a lot of people around there. So public announcement, this will be a vegan, no template-alias programming presentation, so you could sit and relax. Let's start by a small amount of poll. Is there anybody in the room which in his professional environment is still stuck with pre-C++ 11 C++? Okay, so let's make a prayer for all those guys and girls. So how many of you are actually currently building, let's say, a production-ready software systems, whatever, using C++ 11? Well, quite a bunch. C++ 14. And who is, like, how to say that? Who would like to live in danger and is still producing production-ready software using C++ 17? Great. Okay, fine. So you too, you can go actually. So, so now the question I will try to ask and try to find an answer around is. What if you are stuck in a situation where, for different reasons that we will go over, you have no access to some of these modern C++, recent C++ features, the notion of modern C++ starting to be fuzzy. So why I'm speaking about that, so we, at Numpscale, we try to build highly performant, highly efficient tools for people, and we make a choice to try to write this software with a minimum amount of technical depth by adopting the most efficient version of C++ for the given task. We understand that by being a startup, we have the choice and we have the opportunity to do this choice, but it's not something that could be doable in any organization. So I wanted to go over a bunch of things that happened to us at some point before we migrate, and how you can actually sell to your management / computer science department / whatever boss the fact that you need to upgrade, and this upgrade needs to be done quickly. So I will let you interrupt me during the talk if you want to ask questions. Don't hesitate. And so let's start. So, well, what was the problem actually? We are probably at the best place in time to actually do cool C++ things. So there is a large amount of interest and momentum around the current version of C++, the next one, and starting soon, the next one. So there is a lot of things going on. So it's a lot of experimentation that leads to very cool new idioms and practices, some you may have seen this week or last year. And the language itself is getting easier to teach, easier to actually reason about. It's more workable than ever. So the question is, why not is everybody still doing C++ 14, 17 already? Well, the question is, it's more a cultural thing than something else. So the solutions are not that much. Indeed, you can actually make some kind of lobbying, so you can switch to whatever version of C++ you want to go, or, which is a more radical thing, so you can get a new job elsewhere, or, well, you can, drop the ball and do something completely different as a source of income. And so if you have any questions, thanks for coming to this talk. Of course, I'm not serious, of course. So if you are not that radical, well, what's the actual question? Well, what is preventing people to migrate to new compilers version or new compilers altogether? Because sometimes it's more than just changing version, is switching from GCC to Clang or GCC to, Visual Studio to GCC, thing like that. So it has a real impact which go beyond the simple technicalities of the language. You have a huge cost, you may have a huge cost to change your compilation stack, your compilation build system, whatever. And those fundamental changes are some things that companies or organizations may be wary to do because they put them into an unknown situation about how many times before my production-ready code start compiling properly again. There is also a bunch of latency between the fact that the standard is issued and it's available in a given compiler, even if it's done far, far faster since the last couple of years. I remember, maybe you saw it, I think when C++14 was ratified, you could actually check the Clang Twitter live during the vote for the paper to be integrated in C++14, and the tweet goes, paper this much is accepted, and the next tweet was, oh, paper this much branch merged into master. So depending on the compilers, it goes faster than maybe others, but you always have this small lag between the time the thing is act and the time the thing is available on your computer. And for maybe most of us that work with, this species of humans that we call clients, sometimes they have, like requirements that we know make no sense, but they are clients. So we need to fit with whatever they want. And sometimes you cannot deploy your new, shiny tools built with the latest whatever because they run on a silly aging platforms or of compilers versions. So what are we actually losing? And that's the point I think if you want to use this talk and slap it on your manager's head, is you are losing a lot of things that can actually be translated later into cost reductions. The code is simpler, and which means it's probably smaller, and if it's smaller, it's probably far easier to manage and maintain. It's more expressive, so the amount of errors you can put in it because you misinterpreted something or you miswrite something is less than usual. And I mean, if you make this jump now and not in 2015, when the C++30 will be, like acted, when we're still compiling in C++ whatever, you have this technical depth that will be massively reduced. And to illustrate that, I picked a bunch of features from latest C++, which I think are actually interesting, both on the language and on the library side, and just to make some kind of comparison between a bunch of compilers. So this is numbers I found on the CppReference.com website. So if this is wrong, well, we can blame them and edit the wiki later, but whatever. So a bunch of things that you probably saw already if you went to either Jason or Kate talk is the fold expressions, the Constexpr f, and all the generic /variadx lambda functions. That's three of the very coolest things that C++ can now provide. And if you look at how they got into different compilers, you see that there is a lot of, like timing things between versions, and some compilers still doesn't support them altogether. I mean, if whoever from Microsoft is there and this is wrong, just tell me. It's done? Next release. Okay, next release. So 20 or 29 point something? 19.5. 5, okay, so. I will update that. So that's something, yeah. I mean, it's coming in. Nobody is actually slacking off, but I mean, you have an intrinsic time between the time is gone. And same for the library version. I tried to find some information about std-void-t, but I didn't find any. So I think I saw Walter around there. Do you know, Walter, which version of GCC still is the first to get your support for void-t or something?
It's been well over a year, 2 years maybe.
Okay, so it's old, probably 6 something.
There a long time.
Okay, I will check that then. So, yeah. So you got all these things, but what happens if you are stuck with none of those versions? When I submitted this talk, I made the assumption that 1 hour will be enough. And then I thought about the fact that if I want to fit what I want to fit into this talk in 1 hour, we have to make some basic hypotheses, which are the fact that we will make the hypothesis that you live in a world where you have access to C++11 on a daily basis. If not, well, send me an email with your home address. I will get some flowers delivered or whatever, because you are in a really, really bad situation. So let's say you have C++11 available, and you really, really want to play with the C++14 or 17 cool things, and especially the language features, because a lot of library features from C++14 and 17, you can find different versions of this already written in in library like Boost or the Google thing we saw yesterday, or was it the day before yesterday? So the library utilities things is more or less covered, but the language features is what is probably missing. So we try to go over a bunch of those features, try to explain what they try to bring, and can we actually, make some things that look like what they should be looking like, and try to understand how many times you will be spending doing this instead of using the real thing. And we will be more specifically targeting 4 things: the polymorphic lambdas, fold expression, and Constexpr if, which are, I think, in my opinion, the main things that you should be using right now. And we will take a look at integer sequence. And if you remember what I say at the very beginning of this talk, that it will be a template metaprogramming free presentation, well, I lied. So let's go over that. So polymorphic lambdas. So I think everybody is more or less familiar with what the lambda function or anonymous function is since C++11. It's this shiny, small, anonymous block of code that you can put into a box and lay around and call like it was a function object whenever you want it, except instead of having to write a huge amount of boilerplates, you have this very terse syntax, okay, which may or may be not that elegant, but that convey exactly what this thing is. It has this kind of parameters, which looks like a function. So is it working? Oh, yeah. Fine. So you have this thing that looks like function parameters, and then you have a block, in which you have like the code you want your function to be calling. You can pass an arbitrary number of captures from outside, so you can use function derived from outside the lambda inside it, and so on and so on. It's very cool because this notion of locally defined function makes a lot of code far more local, and especially in the case where you want to use algorithms from the standard library, you don't really want to have a function or function object lying you don't know where that you will have to instantiate over there. This line is self-contained, okay, and you know right now that you are calling this function on each element of this vector, and all the information is there. That's a very cool aspect of lambdas. C++11 provided this version of lambda in which the type of the parameters has to be concrete, and C++14 lifts this by letting you have polymorphic lambdas and variadic lambdas, which means that you can actually have something that will basically behave like a templated function object, a function object, with a templated function call operator, which can be variadic if you want. And instead of having a huge mess of template something around the lambda, we decided to use this auto thing, which basically say I can be of whatever type you want. You can have any number of such auto, and everything will resolve to a different types. It's basically a templated lambda without all the syntactic crap you may have to want, which brings the lambda up to the level of expressivity of regular function. Okay, fine. We can do this. This is an example of a a variadic lambda. So yeah, sorry. You can basically do this ... things. Like you would be doing on the normal functions. This notation also gave birth later to a proposal to be able to write that for a regular function. Yeah, okay, fine. What if I only have C++11? Well, sad. You don't have many choice. If you want to have a polymorphic / variadic lambdas in C++11, you're basically down to write a custom function object. There is no easy way to do that. Well, you can write it like this, but this is actually a bad approximation of what the lambda was doing before, and the real thing is far more complicated, because what if I is of a type that when you multiply it by 3, you get another type, and when you multiply it by -1, you get another type, which is not t, so you may end up with something like this, where you use the trailing return types deduction to get the things right. So that's not something you really want to write, but, well, that's all you have in this case. So the pro and cons are rather straightforward. The pro is that the implementation is rather straightforward. It's basically what you were writing in C++03. The second point is that this list of pro is rather short, so I can go to the cons right now. it breaks the locality of the code again. 99% of the appeal of lambdas function is that you make everything local into your code side. And having to go back to write a function object somewhere, instantiate it, and so on, makes everything awkward again. But, well, if you really want a completely generic lambda function replacement, you're stuck with that. But there is an interesting case, which is the case where what you really want to have is it's not really a polymorphic, completely generic function or lambda function. Actually, what you really want to have is have your lambda function work with a small subset of different types that you know already, but the only thing you can write is actually write this auto thing, so the lambda capture whatever. So there is an interesting technique that was proposed by Dave Abrahams ages ago, which I found rather interesting, but not that much used everywhere, which is to use the fact that the lambda, when it gets compiled, get turned somehow into a function object structure and then a function object instance. And if you look at the standard, it basically says that this thing actually is a structure. Okay, it's a type, it has an operator, function call, and so on. That means that you can use it like any other structure. And the funny thing, for example, is that you can take a lambda as a struct and build something out of this type, which is, it has a strange name, you doesn't know what it is, you doesn't know how to handle it, but you can write something like this. So this structure takes two other types, which inherit from them, and you take two instances of these F1 and F2 things, and you just forward them into your parents. And you say, okay, now I want to use the function call operator of both of them at the same time. Fine. But what do we do with that? Well, you can write a function like this. Then again, that takes two F1, F2, and builds this poly of F1, F2. And return you this bag of things that happens to aggregate those function call operators, which leads to some things that start to look like a better approximation of a lambda. So you can write something like this. So you can say, yeah, I want to build a function object, a local function object, and I want that if you pass me an int, I would do something. And if you pass me a float, I would do some other thing. And this thing is wrapped up into a type. You don't really want to know what it is. And you get your f. So I put it into a f, but I could take this return from poly function and call it from an algorithm or whatever. And it will basically act correctly whatever the type the value you pass there, and we just select the proper overload. It's like you build a function that aggregates an overload set into a box, and you can use this box afterwards. And the funny thing is that there is nothing in the definition of the poly function that make direct reference to the fact that F1 or F2 has to be a lambda, something you cannot check, I think, anyway. It just waits for something that behaves like a function. That's cool because the return of poly is actually a function itself. So you can make a second overload for poly, which is valid one. And you say, yeah, if you give me, if you give me a whatever number of function things, I would just, recursively pack them into a poly of poly of poly, And every level of those poly things would just repropagate this operator function call up to the other one. This means that you can basically add an arbitrary number of those overload sets into this poly call and get this lambda lookalike object, which is defined locally, like a regular lambda. It's not fully generic, because you have no way to actually say, and for all of the type, do whatever. But you can actually reuse this in the case where you have a meaningful set of types you want to support into your polymorphic lambda. So what happens if you want to use this? So if you go through the fully specified polymorphic lambda code using the function object and things, well, it's probably what you are already writing because you have no other option, especially for the poor lads around there, which is still stuck in the pre-C++11 world. It destroys the locality advantage of the lambda, which is, I think, the worst actual disadvantage of this. And you will need a non-trivial amount of rewrite when you want to switch from this to an actual lambda. But this rewrite is cool because you are removing code, and removing code is the thing you want to do anyway when you refactor, so that's fine. And as for the poly solutions, as we have this locality back, we can actually use this in a more open-ended way, and the impact on the rewrite would be a bit less. But the question is, one of your coworker comes around and provides you with this piece of code. I mean, the poly structure and the two variants of the poly function. Questions: how big is your, let's say, developer group's reluctance to let that pass a code review and be integrated into your actual production code? That's the main issue with these fixes. You need to convince the people that we work with that it works, you do what they want to do, okay, and they can put it to a box and sleep on it. That's the main issue with these kind of things. It may make a bunch of people uncomfortable, especially because it looks like it doesn't do anything, yet it does something. And you have probably a bunch of work about explaining what this thing is doing. Okay, now, let's have a look at fold expression. So fold expression is based on the fact that Viadic template, by introducing this ... code expander, made a lot of code far more easier to write. So the ... thing, which can be used as a declaration of a Viadic pack, is also the syntax for expanding this pack into something. And usually what you have to do is either you can express your Viadic code into something you can expand naturally, okay, which every element of the pack would be expanded one after the other, separated by comma, or you're stuck in writing something that looks like a recursive descent over the structure of the Viadic pack. So these glue things is actually very interesting, but what if we can't or we don't want to use these comma gluing things? Or if the recursive descent of the structure of the pack is so bad that it starts affecting compile time. And fold expression was a way to try to solve these expressiveness issues. So you can actually use ... on a lot of binary operators, on the left, on the right, with the proper semantics that it means, with the proper default values that it requires. And so, for example, if you want to write this simple all function that takes a bunch of arguments and try to logically end them all together, well, it's basically a one-liner using fold expression, which is very cool. And you can just call your all function on that, and this ... end args just expand to that. And that's exactly what you want. Okay, fine. What can I do if I don't have fold expression? Well, first reflex that a lot of people have when they try to deal with Viadic pack, which is wrong, is to say, yeah, I'm just use this recursive version. That means that I can do something like this. I have a terminal case. That means that if I call all on a single parameters, just return the whatever the thing is. And if I have more than one, it's probably that I have one and a bunch of others. This is a traditional structural head and tail separation. And I will say that it's the head and the result of all applied to the tail. Of course, this probably requires a bunch of universal reference and forwarding and whatnot, just for the sake of the example. It works, but it has a slightly side effect, which in some cases can be an issue, is how many actual function is getting compiled by the compiler. You get one for each step into the recursive descent plus the terminal cases. If you call this function on a regular amount of values, it probably won't register on your radar, but that's something that may cause an increase in compile time, and sometimes it's the basic culprit of this technique. A funny thing is that at some point, I think it was around 2014 or something, I don't remember, quite a while ago, this thing popped up on Twitter. So I don't remember the exact order, but I know that Eric Niebuhr and Sean Parent and a bunch of others was involved, and they basically slapped, Git content to the face of one another. And the question was, can I write a Viadic function that takes an arbitrary number of arguments and a function object, and I want to apply this function to all my Viadic arguments, and I don't want to do that recursively. Which brings us to the 6-foot-long thing. Okay. So does everybody understand what's going on? Me neither. So let's go over it. So what does it do? It plays on the fact that ... as a code expander generates things separated by comma in a very limited subset of context. One of these contexts is whenever you want to build an array or you want to build an initializer list. So what this thing does is, for every A in the pack, okay, I'm forwarding it, and I'm passing it to F, and this function will process my A. It will return whatever, I don't care. And just to be sure it doesn't blow the world up, I will just void this result. And I will go over the other one. But initializer list await for a single type of value to store. So to be sure, we end up in the cases where every element after the expansion of the pack is something that initializer list can hit. We use the comma operator to say, yeah, do that, okay, and just return 0, okay, with a proper number of parents and void and things, so everybody is happy. So what we are doing there is calling f on A, triggering whatever this means, okay, and putting a 0 into this initializer list. And we do that for every element in the parameter packs. And then we have this comma f, which is just there so we can actually return a copy of the original object function, just in case this function object has a state that needs to be maintained and returned. That's probably one of the things you want to put into a box and sit on it and never open it again. But it works. And so that's basically generate a code which is, if you have A1, A2, A2, A4, it basically do f of A1, f of A2, f of A3, up. And you will probably just, ignore everything and you will just stay there with a proper number of function calls. So that's cool. So that's the generic application. And so we can actually use these tricks of using the expansion into a list of comma-separated things of ... to do whatever we want, as long as we find a way to put it in the box that is able to support it. So one way to write this old function that we saw earlier could be this. So we have a result which is true, and then we do this initializer list of thing, okay, in which we say that we update result with a result and the current value in the pack for every pack. And as this thing is a bool, I don't have to do the comma 0 or whatever. I can just store that into a vector initializer list of bool, and it's okay. Okay, do you have any issues with this? I mean, will it work? Do we have any issue with ordering the evaluation of all the subparts? Sorry? Yeah, you have the initialization order, but does it pose any problems there? Yeah, it's probably slower than it should be, because we want short circuit, okay? But it works. And comes the refactoring brigade. That probably says that you can write it this way, by reusing the for each arc thing, by passing the lambdas that do the correct thing on the results, and passing all the A. Both versions are probably as correct. I like this one because you don't have to know about the initializer list fiasco, whatever. You can just put that into the for each arcs box and call it a day. So the what's the impact on the code? So the recursive definition will create a preposterous amount of function specialization you don't really want to see, and the compile time may be a problem. For the for each arc, that's actually far easier because you can keep the exact same interface for this function. You will have one function with no crooky specialization. And you can actually abstract away this notion of I'm just repeating something over all the elements of a pack of things, which is actually far better because we can now build things on top of this abstraction. So next thing is Constexpr if. So Constexpr if basically allow us to write code that can depend on the compile time condition and be sure that we will only compile the branch of the if that makes sense with respect to the compile time condition, which help you write code where you can make decisions about an arbitrary threats or an arbitrary integral constant and write codes that may depend on the existence of an interface or whatever without having your compiler to blow up. It helps into refactoring a lot of code that use techniques like SFINAE in a bad way. It opened up for a bunch of optimization opportunities. And you cannot just use regular if with a static threat because if will compile both branch anyway, and you will be trapped. So what you can do is, for example, you can have a type T coming up, and if this type supports some interface, well, then T will make you a sandwich, and if not, you just return T. Of course, if you call that with a type which has this make me a sandwich interface, it will compile the first one, and then no problem. And if you pass an int or whatever, it will only compile the second branch and call it a day. If you are trying this with regular if by thinking that the compiler will elude the fact that the constant is always true or false, it won't work because both branches will be compiled. So what happens if you want to do this without Constexpr if? Well, you can do what every people did before, which is SFINAE by using the enable if threats by forcibly generate a valid or invalid function definition depending on the condition, and the function will contain the whatever branch of your if. It's a bit complex to handle as soon as the condition starts to be complex themselves. It can be a very tangled web of yes, no, 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 yes, things, and the problem is you are not sure that everything is correct until you tested all the combination and you catch all the cases that were ambiguous. Moreover, this thing has a compile time which is linear with a number of alternatives because before selecting the correct one, the compiler will have to generate everything and try to resolve the overloads. So another way to do this is to use stack dispatching, which is basically integrate the selection into the function overloading itself, turning that into a compile time which is constant time and makes the things a bit simpler because you don't have to deal with this enable if fiasco. You can just list every cases you want to support and have a way to select the correct one in one scoop. Those two things are a bit more complicated than they should be because they require you to write a huge amount of helper functions, but that's basically what you need to do. So we will just waggle our magic wand for a while and turn this into, something a bit better. So the idea is to look at what Constexpr is doing. Constexpr if take a condition at compile time and select between different code fragments. And this fragment has to be compiled conditionally. So the idea is to say that we have a tool to generate code fragments, that's lambda function. And so we can basically take lambda functions, SFINAE or tag dispatching, smash them together, and have a nice approximation of Constexpr if. This notion of lambda being a code fragment that you can carry around, it's a talk in itself. It opens a lot of techniques which are very interesting, but let's focus on that. So what can we do? Well, let's take the code we have just before and look at what we can do. So I will start from there. So we have this Constexpr if thing, which is now a function that takes two things, T and a F, which is the true and the false cases, and takes something which is a type there, C, which contains a condition. And what you do is you pass that to a select function, and the select function uses SFINAE to select which version of the function will be. If the condition is true, I will take the path of the function that returns me the true value, T, and if not, I will get the false one. And once I got that, I make the assumption that these T and F are actually function objects that take no parameters on their function call, and I just call them directly, and I basically execute the one true or false branches. So you can use it this way. So you can Constexpr if on the fact that is T is integral. If yes, you will be nice to generate this, to call this code, and if not, you will call the second one. Well, fine. Except this code is half of what Constexpr if should be. Do you see why?
You wouldn't be able to compile if the T didn't have a thing.
Yeah, so now imagine that instead of just printing things, I put back the return t, and return t make me a sandwich. And I pass an integer, I will get a compiler error because the lambda are compiled on the spot before being passed to the whatever. Well, sad. So what can you do? You could actually make it so you have to wait before compiling your lambdas. So that moves you from C++11 to C++14 because you will need actual polymorphic lambdas. That's one way to solve the problem. There is a bunch of others. If you didn't solve it already, I will advise you to have a look at Vittorio Romero's talks last year about static code selection talk, which is actually take another take at this issue, and which is very interesting. So what do we do? Well, we just make a small adjustment to our code by saying that Constexpr if calls the lambda selected by the select function and pass it something, whatever. We don't care, but this whatever has to be from a dependent type. So for example, you can just pass an instance of the condition types. And what you do is that your lambdas there, well, they now take a polymorphic argument, which is anonymous because you don't care about the value of these things. It just there, so this lambda is turned into a template function object function call, and it won't get compiled until one or the other gets selected. So it's a bit counterintuitive, but it gives you exactly what you want. So this is another example. Basically, I say that if t is arithmetic, I consider that I have one element inside, and if not, I will just try to call size on it, and I will print the size of the thing. You can actually combine that with whatever kind of threat you want, and you basically are where Constexpr if is. It's not that ugly as soon as you put everything we saw before in the box, okay? It looks like, the thing you will be working. Now that I think of it, I should have called this thing if_Constexpr, because so the migration path could have been easier, but that basically is this. So if you want to turn that into an actual Constexpr if later, just have to remove the underscore somewhere, put parentheses on it, and replace the function call things by brackets, and you're done. I mean, brackets, and you're done. So, well, you have that, and you have this explicit finite type dispatching things, which could be cool because you probably already wrote that already because you have no other way to do it. So, but as I said, it requires a huge amount of functions and function helpers and specialization and whatnot. It makes the code unnecessarily big, and it makes the refactoring effort as much as large afterwards. The small emulation to the rapid selection into a box is actually better. You can actually make it as close as possible as a Constexpr if syntax that you want. Vittorio's versions use square brackets and a dot notation to do both branches, which is quite cool. I mean, you can walk around the elegance and the like the syntactic sugar of the thing, and it's done. But you will need polymorphic lambda support if you want to be completely walkable compared to Constexpr if. So now what's left? Well, we have integer sequence. So integer sequence is a strange beast, which come to help you write variable template-based code in a way so it doesn't look strange. So the idea is to have a type which is basically a box of variadic number of integers of whatever type you want, and so on. And this integer sequence basically contains value like 1, 2, 3, 4, 5, 6, I mean, in an order or with a step, whatever. And one of the use cases is to be able to do something like this. So this apply function takes a function and a tuple, and we basically take every element in the tuple and pass it to the function as argument, which is something that cannot be solved properly by just using the recursive nature of the path, because there is no way you can recursively call the function with something and then something else. It won't work. Okay. So the idea is to do this. So you pass the function, you pass the tuple, and you call this make index sequence things that takes the size of the tuple as the parameters and returns something which looks like this index sequence of I, ... And these things, if your tuple, like, let's say, has 5 elements, you will end up with an index sequence of 0, 1, 2, 3, 4. Oh, well, which happens to be the static index you require to get access to the 0, 1, 2, 3, 4th element of the tuple. And so what you do is you just call std_get on I on the tuple, and you unpack that for every I in the integer sequence variadic pack. And so you end up with f of get 0, get 1, get 2, get 3, get 4. So that's a very cool tool, because you can write things like this. You can do the other one, which is actually calling f on every element of the tuple and rebuilding the tuple afterward. I mean, you can do all of this and much more. Well, a problem is that's the C++ 14 features, if I'm not mistaken. Yeah, it is. And it doesn't sound like that easy to emulate. Well, in fact, it is. It's not that a big burden. So what you want to have is, you want to have this in sequence, which is just this variadic pack of integers. And the idea is to say that if I want to have a sequence of integer which is 0, 1, 2, 3, you can basically say it's a sequence which is 0, 1, and a sequence which is 2 and 3 that I just concatenate. And 0, 1 is itself a sequence of 0 and 1 that I concatenate. So you will recursively concatenate numbers until you get your full sequence. So what you need to have is this, what we call range cat, meta function that takes, well, two types, which are the two integer sequence you want to merge, and the start point, which will be the value you want to add to the other one. And so if you have two integer sequence full of I and full of j, you can get one which is all the I and all the j just slided by the value of start. And you can just capture that this way. So it's a bit funky because we keep telling people that, you know, you need to have your variadic parameter pack at the end, and you cannot have multiple of them, which is exactly not what I do there. Because what is important there is what the range cat type definition wants. It just wants two types and an integer. There is no variadic upstairs. There you reuse variadic pack just to be able to construct the specialization of range cat. So we don't care that we have two sequences of int, because the compiler will properly know where they are into the type of the first and the second one. And so we can do this and just collapse everything into a single integer sequence. So now that we have that, what do we do? Well, we need to compute these things. So we have this case where if you tell me to make an integer sequence of nothing, I will just give you an integer sequence of nothing. If you want to have an integer sequence of one value starting from start, I will just give you start into an integer sequence. And if you have more than one, well, I will take your sequence, and I will basically ask you to generate the first and the second half, and concatenating them, starting with the middle of your sequence size, which is basically what happens there. And so we will recursively do this until we end up to 0 or 1, and every value just, concatenates. And once we have that, what you can do, we can make a small template-alias, so you can have something which is far easier to manipulate. Well, it looks like I'm just doing something I just tell you to not do, which is use recursion over variadic packs. There is no other way to do it this way. Or, if you have one, I'm very open to see it because it's complicated. But is it really bad? How many, I mean, if I have for a given n, for a given size of integer sequence, how many types do I need to generate? I mean, we keep cutting things in two in some kind of a tree order that smell like a logarithmic number of things, which is okay. Well, good things is this kind of tools, I mean, you can find libraries with implementation of that in it. You can look at MP11 or Brigand forever. You can actually not have to write that the same way you don't have to replicate the new algorithm or whatnot. I mean, there is probably a library somewhere that already implements that. So, as a conclusion about all of this, you can, with a non-negligible amount of effort, but not that a big one in some cases, you can replicate a bunch of non-trivial language features from C++ 17 into the other language version. Now the question is, should you do it? Or should your effort be into this, like finding a new job or lobbying, or knicking? One of the things we want to show there is that, yeah, you can do it. You can actually assess how big the effort could be, depending on your familiarity with the actual language and whatnot. Now, what we probably want you to do is probably take these things, okay, and if you're stuck with this kind of thing, just reuse these tricks, or use them to actually show, okay, this is all the crap I need to do to make my thing work right now, and it's probably better if you spend this effort changing our compiler version or our compiler altogether. It's probably better for you to try to pursue your whatever hierarchy or whatever boss to make it change, or in the case of our very, nice customers, try to put some sense into their requirements, if you can, and try to actually, use these things as point where you can actually say, okay, this is what it will cost me, and I don't really want to do that because this effort should be put somewhere else. There is a lot of other language features we could have gone over. A bunch of them are actually out of whatever emulation things you can do. For people that are looking at C++ 17 and 20 and things like concepts and so on, you can have a look at things like, for example, the range v3 implementation. You can find a good emulation of concept inside, but which is actually a beast in itself. And as long as the language features start to be more and more, ingrained into the very language itself, it will be complicated to get this emulation working anywhere. So at some point, you will have to build the bullet and jump over whatever version you need. And the other thing that we usually do tell to our customers or the company we work with is, don't do an incremental jump. So there's no need to go to whatever to 11 or from 11 to 14. Go to where you are and go as far as you can into the support of the language version you can, because if not, you're just delaying the inevitable and just hiding cost and hiding efforts. So thanks for your attention, and if you have any questions, I will gladly answer them. Thank you. That's okay for me, But yeah, got one. Nope.
Hi. I'm curious, do you meet the situations where the standard library implementation is not up to date, and how to work around that maybe? Okay,
so the question is, did we encounter the cases where the standard library was not up to date to whatever we need? That's what you said?
Yeah, more specifically, not like missing a whole component.
Oh, yeah.
So signature differs a little bit.
Okay, so like missing components or completely missing a point of implementation. Yeah, it happened to us a bunch of times where the compiler is happily claiming it's, let's say, C++ 14 compliant, except for this bunch of standard library components, which were actually the things we wanted to use. In this case, well, what we try to do is either you try to find a way, if the compiler permits, to tell him to, okay, what about using this version of the standard library? That may or may not work. Depending on the compiler, it could be an effort in itself to get there, because it's probably something which is not very documented or at least publicized in a proper way. In the other case, what we will end up doing is, go and look at the implementation of what we were missing into another compiler and re-implement it. It happened to us at some point because I don't remember exactly what happened, but one of the version of one of our compiler has a badly implemented version of integral constant, which I still doesn't understand how you can actually botch implementing integral constant, but whatever. And basically, there were no conversion operator to the integer types that the integral constant was holding, which is something you have to have everywhere. So you cannot just take an integral constant and pass it to a function waiting for an actual integers. So in this case, I mean, the cost of re-implementing integral constants was basically nothing because it's a very small component, so we just rewrote it. We ended up with suboptimal implementation of standard components, especially algorithm in other cases, because we were trapped between two minor versions of a compiler. And what happened is the patch to the compiler was not coming out fast enough for what we need to do, and we ended up trying to change the standard library that was supported. Whenever this happens, I think the best solution is to try to assess the complexity of the component you need to support, and only rewrite it if it's something trivial that you know that you can write properly. And if not, try to find a way to make your compiler, use another STD version, which may or may not be easy, or, well, try to, bypass the issues by trying to upgrade, but sometimes you can. But yeah, usually what does happen, you're in for some kind of implementation anyway.
Are you aware of open source libraries that offer these kind of abstractions, or do we have to build it ourselves?
So the question is there actual libraries that provide these things? Yeah, there is a bunch. Depending on the thing, I mean, for example, if I take the four expressions, the for each idioms has been published a lot of time, and that's probably your best way is to actually just write something that looks like this. For things like integer sequence, or for example, this polymorphic lambdas lookalike, you have to look at libraries you have a bunch of modern metaprogramming libraries that happens to do all this crazy type manipulation thing, and then things like that because they needed to interface with basic non-type-based code, and so you may find things like this. I don't have any name right now, but I know that I found some implementation of that somewhere. And for the rest, try to have a look at what Boost offers, or things like, what's the name of this thing? I mean, there's a Google thing we heard about. We found about, you probably have half a dozen of such library out in the open, and which with different number of coverage. That's something which is not very, it exists. It's not very easy to find them, but a lot of times they are not that much, publicized, because most of the time you have a lot of people that can just jump over and don't care about having this legacy library to make the thing. Matthew, weren't you working on something like that also at some point? Or do you have that internally, this kind of library that, plugs the all into the standards? Was it you or somebody else? I don't remember.
Sorry, what?
A kind of library that do all this plumbing to uniformizing the...
like the implementation
of whatever,
Yeah, we have something like that internally.
Yeah, so usually people do it internally. That's mostly what I saw, because it's either, most of the time people just need this couple of features, and they think, and sometimes they write that it's better to just write them because it's straightforward. Another thing is that, for example, for the fold expression emulation, you may end up having to write something that work on this principle of making ... do whatever you want. For the very explicit cases you are dealing with right now, instead of just grabbing a generic unpacker and try to fit your stuff in it, and you may end up with better code generation at the end. But if you dig around, I think yeah, you will find a bunch of that. But they are not that publicized.
I have one remark and one question.
Yeah.
For the fold expressions, I think last year Roland Block gave an interesting lightning talk about the various Roland Block from CppCon lightning talk on how to do without fold expressions for getting the truth from all the condition. And I think some of them were easier than the one shown. Oh yeah, probably.
I think you have a bunch of other ways to do that. I tend to prefer the Viadic expander versions for compile time reason, but I may be biased about compile time, so probably not a big deal for most people. I think you can probably do it in a bunch of other ways. I have to watch this lightning talk because it completely went under my radar, so good point. Yeah, you probably have, I can think about one or two other ways to do this. Now, I think in the end, they will probably generate very similar code anyway. So it's probably more than, like personal style preferences or whatever.
Okay. My question was about the flowers. Do you have like a form on the internet where like I put my address, or how do we work that out?
Yeah, you send me a message on Twitter, and we can arrange the flower thing.
Maybe a hashtag or something.
Yeah.
Okay.
Thank you. So thank you very much.